Right, good morning everyone, and welcome to our Computer Vision Roundtable. My name is Doron Joffe, and I'll be hosting the session this morning. Perhaps we can begin with some introductions. My name is Doron Joffe. I work at Optimum Solutions. I am a senior data scientist specializing in computer vision for smart mining and manufacturing. And I've had the privilege to work with multiple computer vision applications and algorithms across the industry. I'm joined by two colleagues, Toby and DX, who have also got experience in the computer vision space, and we will be having a roundtable discussion. Now, I want to emphasize this isn't a webinar, it's not a presentation, it is meant to be a discussion, it's meant to be interactive. So please stop me, ask questions. We want to engage with you. We want to understand what problems you are facing in your industry and how computer vision can try and address these problems and how we can develop solutions together. So please stop me, ask me loads of questions and engage with me. Toby, perhaps you can give a brief introduction about yourself and some of your experience.
Thank you very much, Doron. Good morning, everyone, and thank you once again for joining us in today's round table. Okay, my name is Toby Afolabioluwa Toby, but you can call me Toby for short. I'm a senior data scientist, also with Optimum. I specialize in artificial intelligence generally, which includes your machine learning and your deep learning, computer vision, natural language processing, everything deep learning, basically. Okay, so yes, I think that's it for me, Doron.
Great, thank you very much, Toby. DX, perhaps you can give a brief introduction about yourself.
Hi, thanks, Doron. Just turn on my camera as well. Hi, everyone. I'm Dalukolo, and I'm a junior consultant or data scientist here at Optimum. And a lot of my work has also been focused on the data science space, mainly trying to see how can we use computer vision in industry, and also a lot of research-focused work, seeing what is the future potential of this technology and how can it be best leveraged in industry with your hardware concerns as well. Yeah, thanks.
Great, thank you very much. Throughout the roundtable, I'll be engaging with the team. And again, just to emphasize, we want to engage with you as well. So please stop me if you've got any questions or any insights that you want to add. A brief introduction into Optimum. We work across multiple different industries, such as business analytics, financial engineering, smart mining and manufacturing, which is where I specialize in. We work with digital engineering space, as well as the research, teaching and learning space, so servicing our universities with MathWorks products. We are the official authorized reseller of MathWorks products in Southern Africa. Some of our clients, you can see the broad industries where our clients serve in. We've got the likes of MTN, Nedbank, Sasol, Anglo American. So we cover a broad variety of industries. In today's roundtable, we're going to be focusing on the smart mining and manufacturing industry, but these computer vision applications can span multiple different industries. A brief agenda for today, we're going to have a look at some of the common industry trends that we have seen in the computer vision industry. So what is the status of the computer vision industry? What are some of the latest technologies? We're going to have a look at some data considerations. What we've found is clients typically have problems when it comes to their data, curating their data sets, acquiring those data sets, and effectively handling those data sets. So we'll have a discussion on some data, and then we will have a discussion on some deployment considerations, because there's no point just developing a computer vision algorithm. We need to create an infrastructure or a platform to control that algorithm and integrate it with the client's processes.
Doron, will you make this available to us, these slides?
Definitely, yes. I can share these. I can share the presentation at the end of the session.
Okay, great, thanks.
All right, let's have a look at some current trends in computer vision that me and the team have seen over the past few years. There's this constant debate or comparison between cloud computing versus edge computing. Of course, edge computing is when we deploy our computer vision algorithms to an edge device, such as the camera itself, or such as the piece of machinery itself. Whereas cloud computing is where the detections or the algorithm is running remotely in the cloud. And what we've seen is with the development of processing power, we are able to deploy or leverage edge computing more and more. And that is typically preferred in a smart mining and manufacturing environment. If you think of a mine, for example, a mine, our customers typically have connection problems, and it's very difficult to use a cloud computing type of infrastructure. And with the advent of more powerful GPU systems, CPU systems, this is becoming more and more possible. So we can leverage both platforms, cloud computing, but edge computing as well, specifically in the mining and manufacturing industry. And this has advanced rapidly over the past few years. Another common trend we're seeing is the integration of multiple types of AI techniques. We know the buzzword these days is generative AI and LLMs. LLMs are large language models, such as your ChatGPTs and other such algorithms. And we like to leverage these techniques in our computer vision workflows as well, because we can use our generative AI algorithms to create synthetic data, for example, if the customer has got a shortage of their own data. We can use LLMs and generative AI for automated data labeling. And this has assisted the computer vision workflow drastically, and we'll discuss some of that later on. And then finally, we've seen an increase in accessibility of these computer vision algorithms. They can be deployed across multiple industries spanning retail, hospitality, healthcare, and it's no longer monopolized by large industries with incredibly powerful computing power. Even individuals are able to leverage computer vision in their day-to-day lives. And Toby, perhaps you can come in here. I know you've had some experience with deploying these computer vision algorithms to mobile devices.
Thank you very much, Doron, and thank you for this opportunity. Yes, so just like you've said, deploying AI on mobile devices, the ongoing debate is just what you've said. Should it be deployed over your phone, which is edge AI, or should it be deployed over cloud, which is the cloud-based AI? So, but both of them, you have to look at the pros and you have to look at the cons. AI generally are that they are very computational intensive. That is, you need a lot of computation power, you need a lot of RAM, at least 4 gig RAM, and you need your hard disk space also. So the debate has been, should it be deployed on edge or over the cloud? But I'll just talk about the advantages of deploying over the edge and as compared against the cloud. Now, a major advantage, deploying over the edge is that you don't have to worry over data issues, data security, data issues, which is become something big today, because all your data will be stored locally on your device or your mobile device. However, deploying over AI over the cloud, the advantage is that you do not stress the computation ability of your phone. You are not putting your phone battery under stress. You are not putting your RAM under stress. So those are the things that you have to consider. Do we want to are we looking at data integrity? Are we looking at speed? And then are we looking at connectivity? Just like Doron said, if connectivity is a problem connected to the server, then I think deploying over edge is the way to go. And then there's also this platform that we also use, the ONNX. The ONNX is an acronym for Open Neural Network Exchange. Open Neural Network Exchange. Now, the advantage of that is it helps you to streamline the process. It helps you to prune your model. It helps you to move your model from one platform to the other. Maybe you're moving from TensorFlow to Caffe or to the different platforms. It's very easy. Once you have your model in the ONNX format, you can move it from one place to the other, and it's very easy to use on your mobile device. Yeah, so those are the trends that we've seen, and thank you very much, Doron.
Great. Thank you, Toby. And that's a very good point you raised. We had a customer a couple of months ago in the mining and manufacturing industry, and they had a handheld thermal camera, and they wanted to do video analytics based on the output of this thermal camera. Now, that had to be deployed. This algorithm had to be deployed to the thermal camera itself. We couldn't have some machine sitting somewhere in the control room. The operator wanted to see the output immediately on the thermal camera screen in front of him. And we had to use platforms such as ONNX to do the deployment to the device itself. And this is something which the computer vision industry, this is where we have advanced drastically over the past few years. We no longer need huge computing power to do and run these algorithms. We can deploy it to handheld devices, and that is something that is incredibly useful, specifically in a mining and manufacturing industry. So we're going to have a look at two common use cases that we typically see in the mining and manufacturing space. The first use case is what we call a virtual fence. So typically there are regions which we like to refer to as exclusion zones. That is a zone where an operator should not be operating, or if the operator is operating in that zone, we need to deploy some form of interlocking system to ensure the safety of that operator while they are in the zone. So we would have a CCTV camera pointed at that zone, and the CCTV algorithm or the computer vision algorithm running in the back end alerts the control room when an access breach has been detected. And of course, a very common use case is what we call event detection. So detecting dangerous conditions in a particular space. So you can see the image on the right, I have blurred it out for privacy reasons. This customer had a particular machine, and a leading indicator of troubles or defects in that machine was this heavy smoke and sparks. Now, this was a very fleeting event. A smoke event could occur over a period of, let's say, 2 or 3 seconds and then die down, and the operator would often miss that event. However, a CCTV camera aimed at the area of interest will never miss that event. And again, we would integrate this into the control heuristics of that particular plant, so we can alert the operator and interlock any processes. So these are the use cases we're going to be discussing, and we're going to have a look at some of the challenges that we faced when we were developing these algorithms. So let's have a look at the data considerations for these particular use cases, because this is typically where the biggest bottlenecks of the computer vision workflow occur. The first problem we find is data acquisition. So we are getting this footage from a CCTV camera. However, we need to train our model. Now, hopefully, these explosion events are very rare. They perhaps happen once a year, twice a year. So the data is very limited. We have only got a few instances that we can train our model on. And it is very difficult to build a robust model when we have got this imbalance within our data set. And this is where Gen AI will come in, as we will see on the next few slides. We also have the problem of data labeling, because we don't want to sit here labeling multiple images that can be very time consuming. We would rather focus on the model development. And of course, we need to monitor our model in production, because we don't want nuisance alarms to be occurring once a day, twice a day, because then the operators will lose confidence in our solution. If we are generating a false alarm, then when it is a real alarm, that alarm would be ignored. So let's have a look at some of these challenges and how we overcome these challenges. So the first challenge we said was the data acquisition, getting enough data, and this is where our synthetic data generation comes in. So the top image in the top left corner is an actual image coming from the camera. Now, we have only got a couple of those images because these events are so rare. But we use our Gen AI networks to synthetically generate additional images to build up our data set. And you can see the synthetic image is very, very good. You wouldn't be able to distinguish between the two if you were just looking at it. And this way we can build up a very large data set with a very few very few samples as a base data set. The same goes for the two sets of images at the bottom. We had a customer who came to us and said, we need to classify certain types of rocks on a conveyor belt based on color. They also had a very small data set because they had recently installed their cameras. What are we going to do? We are going to use our synthetic networks to generate a much larger data set of synthetic images, and we can train our models on this synthetic data. Toby, you've got some additional experience with data augmentations, another technique for building up a larger data set. Perhaps you can jump in here and explain that.
Thank you very much, Doron. Yes, so a big part of data, deep learning, machine learning, data transformation is augmentation. Now, augmentation is needed, is a technique used to artificially increase the size of your training data, okay, by performing some transformations on the data that you already have. So transformations like rotation, like flipping, like scaling, like color jittering, like, a lot of transformations, noise injection. So you have little set of data to start with, but you take a fraction or a part of this little set of data, and then you perform transformation, different types of transformation, and then you create more data sets. Now, the advantage of this is you build a model that is very robust. Okay, you build a model that's very robust. That's number one. Then number two, you mitigate the chance of your model overfitting on your small data sets, because when you have very few or very little instances, your models will tend to overfit. That is, they just overfit. So you mitigate that chance, or you stop that from happening by data augmentation, reproducing data sets, okay, based on what you have, but just transformations of the original data set. And it's a very well-known process in deep learning pipeline, and it has really helped a lot. Yeah, so thank you very much, Doron.
Thank you, Toby. And I think it's particularly relevant in a mining and manufacturing type of environment when we see such diverse conditions in deployment. For example, I'm currently building an algorithm that monitors the motion of a particular piece of equipment. And a couple of weeks ago, the customer installed a type of flashlight on top of this piece of equipment, and the lighting conditions changed drastically. Now, without a robust model, that model would become very confused because the lighting conditions are very different to the data set that model trained on. However, during the augmentation process, we synthetically generate images that have got very diverse lighting conditions so that our model can be exposed to different conditions at training time, and then these diverse conditions that we see in deployment will not affect the accuracy of the model. So data augmentation has got the advantage of building up the size of the data set, but also the diversity within that data set. So these are two very useful techniques that we often use when it comes to the data pipeline. I've included a very powerful quote from Andrej Karpathy here. He is probably one of the most famous computer vision data scientists that exist. He worked with Tesla. He then worked with OpenAI on their ChatGPT program. He is what many people would refer to him as the pioneers of computer vision. When he was running the AI Tesla program, he had an interview and he said over time, Tesla has grown to a more than 1,000 person data labeling organization that is full of professional labelers. And there's a lot of mystery surrounding the AI Tesla program. But essentially what it is, they get all this video footage being streamed back to their headquarters from their cars. A Tesla car has about 8 or 9 cameras around the vehicle, and those cameras stream data back to headquarters. That data needs to be labeled by humans. So those humans will sit there and they will label other humans on those images. They'll label trees, cars, dogs, cats. But their entire workflow is dependent on data labeling. And Tesla, over the past couple of years, have been trying to automate this process because it is an incredibly time-consuming process. And if we can try and automate this process, we can optimize our computer vision workflows. And we have experimented with different types of data labeling automations, which we'll discuss now. We have what we call a grounding dyno model. And a grounding dyno model is a zero-shot detector that combines speech and vision capabilities. A zero-shot detector is a detector that requires no training. It has been trained on millions of images in the past, and we can leverage that detector for our own labeling tasks. What we do is we pass in a text prompt to this model, and we ask this model to find that object within our image based on this text prompt. So for example, if we're analyzing our use case of smoke and fire detection, the text prompt that I put in over here is smoke. I gave it a few thresholds, and we found the smoke in the image. That required no human intervention. That was our grounding dyno model doing the labeling. Now, because we are leveraging the power of text, we can be far richer within our text descriptions. So I don't want to just find the apple in an image. I want to find the red apple in the image. And because I'm using text, I can use the word red and ask my model to find the red apple. In the image on the right, a more mining and manufacturing type of use case, we're going back to the example of our rock classification. We want to identify the grayish rocks within our image, and of course our text prompt would be a gray rock. So we can use this network, this grounding dyno model, to rapidly label a very large data set based on just text prompts. DX, you've got some experience with different use cases and how you have used this technique in your computer vision workflows. Perhaps you can come in and describe it.
Thanks, Doron. Yes, I have used zero-shot object detection models before. So in my case, I had a client and they were trying to get into the autonomous vehicle space. And so what they were trying to do there is build data sets to train these models that would then live on vehicles to support autonomous driving. So if you think about these images are pretty simple. So if you think about it, you just have one object you are labeling in each of these images, whereas in a driving scenario, there's a lot of various objects. There's a tree, there's a person, there's another car, there's 5 more cars ahead of you, there's a robot, and you want the model to be able to detect all of this. So on a single image, you could easily be labeling about 10 to 15 types of objects, and you can just think about the different sizes. So it becomes a job on its own. So it's no surprise that the Tesla engineer actually said they have a whole team of labelers. It can become pretty tedious. And so how we implemented this is that we used the grounding dyno model to then create sort of a first pass to generating data. And then the advantage of the MathWorks tools is that they have labeler apps where you can now more interactively deal with some of these workflows. And so by using grounding dyno to create those initial labels. So in grounding dyno, you could say label a person, a car, a tree in the scene, and it will try its best. Of course, there will be some misclassifications here and there. And then by connecting that with the MATLAB labeler applications, you can easily just change the label. So that would typically involve a lot of resizing of some of the bounding boxes, deletions for misclassifications, or adding a bounding box that it may have missed. For example, if you see on that picture on the right, if you asked it to label all the rocks, it may miss a few. So when you then connect this with MATLAB, all you'd be doing is adding those missed bounding boxes. And so you essentially reduce the workload by about 70%, I'd say. And so we've implemented this workflow onto up to 30,000 images and never needing to label something like more than 1,000 images ourselves. So you can just imagine the amount of work that has been reduced by that automated labeling workflow. Yeah.
Great, thank you very much. Yeah, it's an incredibly powerful technique. So I wouldn't call it automated labeling. I would call it a semi-automated labeling procedure because we still need the human to quickly check that the labels are correct and perhaps slightly alter some of the bounding boxes in the case of any misclassification. So a very powerful technique. Perhaps we can have one last point on the data considerations, and this is a technique which we call active learning. I'd like you to have a look at that graph in the bottom right corner. There's been a lot of discussion about the size of a data set that we need to build these algorithms. And when we sit in the first meeting with a client, it's almost always a question that we get: how many images do we need to build this algorithm? And typically the customer is thinking 10 or 20 images, and we're thinking 10, 20,000 images. But either way, how big is big enough? Now, there was a study done recently that said if you want to reduce your error from, let's say, 20% to 10%, you would actually need to increase your data set by a factor of 4. So if you have got 20% error in your current model and you want to reduce your error to 10%, you would have to increase your data set from 10,000 images to 40,000 images. So there's this exponential relationship between data set size and error, which means we would need to increase our data set by a factor of 4 in order to get a marginal increase in error, or a marginal decrease in the error of our system. However, if we use a carefully curated data set, that scaling law reduces rapidly. So if we have carefully selected samples within our data set, we maximize the quality of our data set, we can get away with using a much smaller data set. And in order to do that, we use a technique which we refer to as active learning. And active learning is an iterative process. So we would start at the top with an image data set of, let's say, 100 images. And we will train an initial model, which we will refer to as our weak learner. Because the model has only seen 100 images, it's going to be a weak learner. We would deploy that weak learner, and we would ask our model to make inferences in real time in production. And we will monitor that model, and we'll collect the confidence scores of our model, because these models output the prediction as well as the confidence of that prediction. Now, if you look at that example on the bottom, we've got 4 images. We would collect image 2 and image 3 because those are the 2 images where the model those are the 2 images where the model performed poorly. We would take image 2 and image 3, and we would feed that back into our original data set, because that is where the model needed further learning. There is no point of feeding image 1 and image 4 back into the data set, because the model was very good at predicting those particular images. And this way we can build up a data set of only the most useful data. We don't want to populate our data set with data that the model is already good at and doesn't need to learn on. And this way we can build up a good data set, a relatively small data set, but because it has been highly curated, it is a good quality data set, and we can still build a very robust model. Perhaps I can pause over here and ask if there's any questions, any insights. Do you have any data problems that you have come across? Any ideas or thoughts?
What you were saying there about curating the data set reminds me of us from the previous generation, where we were more feature designers, not just large model designers. Like a support vector machine would be a similar idea, where you choose your data points carefully, your points that you want to feed into your model that defines the decision boundary very quite carefully because of the value of certain of those points, and then get a much lighter weight classifier from there.
100%. Yeah, that's exactly what's happening in this process. So here it's different because we are training a weak learner first, but there you are pre-processing your data set. And of course, the two can work hand in hand. We can pre-process our original image data set. We can bring out the features within that data set. We can change the quality, the contrast, and all of that. So the two can work hand in hand, the two workflows, but definitely that's exactly what's happening over here. We want to choose and select the richest features within our data set. Great. I'm going to move on to our last topic, and that is deployment architecture. Now, this is where most people spend the least amount of time, and it is a critical error because in our experience, the model development can take about 20 to 30% of the time, and the architecture deployment and design actually takes about 70 to 80% of the time. And if we don't have a well-defined architecture in place to control our model, there is no point of generating our model in the first place. And this is particularly important in a smart mining and manufacturing environment where we need our model to integrate with the control room, with the CCTV camera software. We need to interlock our systems if an alarm has been raised. We need the managers to get automated reports of the previous explosions, for example. So we need an architecture that is fully integrated with the existing systems. And that makes the model development actually much easier than the actual deployment architecture. So this is what a typical deployment architecture would look like. This is describing an edge deployment. You can see there's no cloud interaction over here. Everything is sitting locally on the plant within the mine. We would have a camera on site, and we often see problems with camera qualities, networks dropping frequently because typically a manufacturing environment has got many different cameras all operating simultaneously. And if they're all sharing the same network, we can see network problems. So those are some challenges we need to get around. We typically stream the camera footage into a machine that is sitting in the control room or sitting somewhere on site. That machine houses our algorithm. And then we have got various communication procedures. The first one would be connecting to the SCADA or PLC system so that the machinery can be interlocked in the event of a disastrous event. We automate the reporting procedures so that the key stakeholders can get an understanding as to what is happening on site. And also, very importantly, we need to integrate with the existing CCTV video software because, as I mentioned, some of these events can take 2-3 seconds and then they are gone. There are no sign of those events. The operator needs to rewind the video footage and see what actually took place. So if we integrate with the CCTV camera footage software, we can download that historical video footage, we can rewind the video footage, we can do all sorts of analytics. And what's very important to understand here, this diagram represents a single camera, but typically in production, we have multiple cameras all working simultaneously. The current project I'm working on has got 9 different CCTV cameras monitoring different processes, and they are all being streamed back to this host machine and being streamed out to the CCTV camera software. You can think of your home security system. You typically have a screen that is displaying multiple camera feeds throughout your house. And that is what's happening over here. This doesn't need to be one camera. We can use multiple processes and stream multiple camera streams and perform those video analytics on those multiple streams. So a deployment architecture is where we spend a lot of time and we dedicate a lot of resources to getting this architecture right, getting it optimized so that we can use real-time video analytics. And we have achieved video streaming of up to 40 to 50 frames per second on a particular camera. So if we optimize this process, we can optimize our entire workflow. So deployment architecture is an incredibly important aspect of this particular workflow. Often we get asked questions as to how powerful does my machine need to be? Of course, if you want to achieve 50 to 60 frames per second, you need a very powerful machine, but often that is not necessary. If we detect an event on one particular frame from that stream, that is often good enough, in which case we only need to achieve frame rates of, let's say, 1 frame per second, even 1 frame every 2 or 3 seconds, and then we can raise the alarm. So post-machine power and processing power is not always a factor. We can often deploy lightweight models to machinery that has got a low processing power, And that links back to what we said at the beginning of this discussion, that often we can do this on handheld devices as well. So deployment architecture is a very, very important aspect of this entire workflow. Right. Any questions on any input on what we have discussed? I'd love to hear some of your ideas, some of the problems you have faced in production. Have you had any problems with cameras? Okay, we can sum up quickly what we have discussed. We discussed some common trends. Toby discussed how we can deploy this to edge devices such as mobile phones, handheld cameras, and other handheld devices, which is particularly useful in a smart mining and manufacturing type of environment where operators often need real-time video analytics done on handheld devices. We looked at the accessibility of these types of computer vision models. We don't need major computing resources. We can deploy this to handheld devices, as we've discussed. We've seen the introduction of computer vision algorithms across multiple industries, whether it's smart mining or manufacturing. We've recently completed a project in the biomedical space. We've looked at projects in the retail space, so customer analytics, heat mapping, where are customers spending time in shops, so we can give real-time customer analytics. There's a broad variety of industries where these computer vision algorithms can be deployed. We had to look at some data challenges and techniques, how we can mitigate some of these challenges. Everyone has data problems. It's generally the primary bottleneck to a computer vision workflow. Do we have enough data? How can we synthetically generate this data? And how can we automate and optimize our data labeling procedures? And of course, we need to monitor our model in production. And this is something we touched on briefly. We can monitor our model and get feedback and retrain our model on very useful samples. But something perhaps we didn't discuss is what happens if we have got data drift in production. The lighting conditions might change, for example. Of course, we have got data augmentation techniques which try and mitigate those effects of data drift, but almost always after 2, 3, 4 months, the model will start deteriorating, and therefore we need to constantly monitor that model and retrain if necessary. And then we looked at some architecture challenges and techniques. How can we integrate with the control room so that we build a fully integrated package or computer vision platform so that the operators can get the most out of their computer vision platform. And if you've got any data, you want to get in touch, you've got a camera feed, you've got some images, you want to know how these computer vision workflows can influence your business, how it can improve safety, definitely get in touch. We would love to take you through some demos, what we have done for some other clients, and if we can show you the impact that these computer vision models can have on everyday workflows within your business. As I said, there's a wide variety of use cases where we can apply the power of computer vision. Okay, finally, any other questions, any comments or concerns that you would like to bring up?
Hey, thanks very much. This was very interesting. Yeah, I'm sure all the guys on the line don't have any shortage of problems that they would like solved, or millions of hours of CCTV footage that can be analyzed. Just remind me about your commercial model and what's the different options for us if we want to engage, as well as whether it's MATLAB specific, or are you looking at other tools as well?
Yeah, so that's an excellent question. As I mentioned previously, we specialize in MathWorks products, so the entire MathWorks architecture and tool stack. However, we don't solely develop within that MathWorks architecture or framework. If a solution requires a Python implementation, for example, we will use a Python implementation. We do like to integrate the two languages together. So for example, that grounding dyno model that DX shared about, that is written primarily in Python, but we like to use our MATLAB apps to assist that workflow. So typically we try and employ a synthesis of the different tools, but we're not limited primarily to MathWorks. We do use whatever tool is going to get the job done and that is going to optimize the workflow. In terms of a commercial model, we do have different commercial models available. Typically, we develop on behalf of the client, and then the client owns the IP of the solution that we developed. So the algorithm sits as a standalone application on the client's machine, and the client owns that solution. We can maintain that solution if necessary. We do have different commercial models available. We are flexible in those commercial models, but again, we're not limited to the MathWorks tool stack.
Thank you.
Thanks, Doron. If I can add, I think, one of the ways that we engage with people is to understand what they need. And sometimes it's capacity or skills. And so we do offer training programs as well as application assistance and coaching, as well as software development and consulting. So there's really a wide range depending on what you need. And so we just have a chat and then we understand better what you're looking for. And we try to match up with that.
Great. Thank you very much. I think we will post a poll at the end of the session. We just ask 1 or 2 questions about how we can further engage with you in some of your needs. So you can take some time. It won't take long just to fill that out. And I will make this presentation available so you can see the slides. You can go through the slides and revisit it. And please do get in touch. We would love to discuss where these computer vision algorithms can influence your business and have an impact on your workflows.
Thank you so much, Doron. It was really interesting.
Sure. Great.
Yes, thank you. It's very interesting. Something I would be interested in is theoretically, I see the good use cases, but like, for instance, the conveyor belt example, your picture just still shows a very deterministic view. If there's something that can do complex analysis on the call or case study in terms of how well it performed, and for instance, how you manage cameras, etc., redundancy, that will be quite interesting to just get info on those business cases.
Definitely, yeah. We can delve into the specific use case and make a tailor-made solution 100%.
Okay, guys, thanks very much. I think I'm going to dial off now.
Thank you, everyone.
Okay, bye-bye.
Thank you. Thank you.